everyone, medical 4700 Kingsway, and it's for breathing problems. Center Mall, acknowledge 3-1.
Engine 31 acknowledge 4700 Kingsway.
Likely you already know that SDR means Software Defined Radio. It works as a USB dongle that captures radio waves, which you then process using computer software. This way we can listen to police, EMS, and fire department radio communications. But what on earth is DEEP SDR? Since it's all software, we can go beyond just listening to the radio. We can process what we hear and visualize it. That's the deep part. And if we need to make DEEP an acronym, it would work as decode, extract, enhance, plot. Here is a demo from a live website.
Engine 7, Engine 1, listen to MVA 4281 Kingsway. That's for a 3-vehicle MVA. 7 received.
As you can see, we can decode what's being said and visualize it on a map. We just heard on the radio that there was a 3-vehicle collision, and this information was instantly processed, summarized, and accurately displayed as a point on a map with the correct pictogram. This is truly remarkable because we can aggregate the data and scale up our understanding of what's happening around us. We can monitor public services and evaluate response times and prioritization. This is our tax money, so why wouldn't we? Received data can be streamed to a website, or it can work entirely offline with no internet access. All it needs to function is the right software, hardware, and electricity. Now I'll walk you through the components that we need to create a system like that at a high level. It starts with a small, affordable USB dongle. I bought one on Amazon for about $50. Mine is a Nginx model, but there are other brands too. I'm not affiliated with Nginx. I just checked the reviews and chose it. The company was founded in 2007 and is based in New York and Ontario. An external antenna is also critical. I bought a bundle that included an antenna, and then I replaced it with a different one I found on Facebook Marketplace. But I also needed to buy an adapter. Actually, my original antenna seemed fine, so I didn't need to buy anything extra. Antennas determine frequency ranges you can capture, so research different antenna types to find the best option for your target signals. This small dongle replicates many features of expensive traditional receivers. It's interesting that SDR devices became so affordable almost by chance. They are based on repurposed, mass-produced television unit chips. Once you have the device, you plug it into your computer. You'll need software to process radio signals. I'll demo two open source projects, SDR++ and SDRAngel. SDR++ is very user-friendly and easy to use. I looked up the local firefighters dispatch frequency, which is 154.4 MHz, and I tuned in. After you plug in your SDR dongle, you can use SDR++ to listen to various radio transmissions, including local public service communications, unless they are encrypted. I am in the Vancouver metro area. Vancouver's police, EMS and firefighter communications are encrypted. However, a neighboring city called Burnaby has its firefighters dispatch communicating over an unencrypted radio, so I can tune in and listen. I noticed that in Canada it's more common to have public safety radio encryption, so if you are in the US, you can often receive more unencrypted traffic. Other important things include choosing the right signal type, and for public service radio it's usually narrowband frequency modulation, NFM. For other radio transmissions it can be different. It's also important to set the right level of squelch. Squelch determines how much hiss comes through. If it's too far to the left, you'll get a lot of hiss between radio sessions. If it's too far to the right, you may cut off the voice and hear nothing at all. Normally existing frequencies are already known, but you can scroll the oscillation bar and inspect what you see. Notice how the fire dispatch has breaks between transmissions. If something transmits with gaps like that, it's easy to miss. I wanted to explore what else SDR is capable of. This is how I learned that most aircraft automatically broadcast ADS-B signals at 1090 MHz. Anyone with an SDR can receive these signals to locate nearby passenger planes, cargo flights and helicopters. SDR++ is not useful for this case, because it doesn't provide a map. For that there exist purpose-built apps, such as dump 1090 mutability. Dump 1090 mutability hosts a local web page that anyone on your Wi-Fi can view using a browser. I installed it and could instantly see aircraft around me with one caveat. My current antenna is a complete misfit for the 1090 MHz frequency, so I could hardly see airplanes around me. There are dedicated websites that track aircraft, such as planefinder.net or adsbexchange.com. They confirmed what I could see. The difference is that of course you don't need the internet to track aircraft if you use SDR, because it's all radio waves. I think it is an interesting feature, and I can see why aircraft enthusiasts find it exciting, or why someone might want to track how often and which planes fly nearby. You could collect data over time and analyze it, unless those aircraft tracking websites already provide that data readily, or it's behind a paywall and you don't want to pay for it. SDRAngel is a very feature-rich tool, but there is a bit of a learning curve to figure it out, and it's much heavier on the CPU than SDR++. I'm doing a demo of its aircraft radar to show its integrated map. I didn't try all of its features, but I read that it also includes a frequency scanner, a weather satellite image decoder, and pager decoding. It can also function as a transmitter, not just a receiver, if you have a more advanced device. I'm focusing just on receiving, and you'd likely need a license if you want to transmit with an advanced SDR. To me, public safety communications feel more relevant, since they expose what happens on the ground around me, which is why I wanted to be able to not only listen, but also aggregate and review the data. I'm going to show what a tool like mine can do. If I search for cardiac, I can see on the map the responses to cardiac events. It wouldn't tell me much at first, but as I accumulate data over time, I can see if there are any trends year over year and compare them to other medical events. I wish I could have collected this information before, during and after COVID. It would certainly be important to analyze. I split the data into several categories, one of which is animal. Metro Vancouver is known for its prevalence of bears, and I just wanted to make sure that any bear events won't go unnoticed. I didn't get too many animal events though, and they are mostly dogs. This one is a bummer, where bear spray was deployed. I find it civilly useful to know how often and where overdoses occur. I've had past negative experiences in areas prone to frequent overdoses. From a real estate and renting perspective, it would be important for me to know whether there is a permanent or temporary shelter in a given location. If we scroll through the map, multiple recurrences of overdose incidents may indicate that there is a shelter or consumption site. Clustering for vehicle collisions works differently. Collisions happen on roads, which makes it harder to place a precise point on a map, unlike when we have an exact address. When we see multiple collisions in the same spot, it's likely that we only know the name of the road. When we get an intersection, we can pinpoint the exact location. Rescue is perhaps a slightly boring category. It mainly covers elevator entrapments. Hazard gets a lot of electrical issues. And Hazmat is full of gas leaks. I won't be reviewing other categories, since it's easy to guess from their names what goes into them. The tool can be used to monitor events in real time and explore past events by selecting a date range. We can also see hourly event counts within the time frame. I've been running it with some interruptions and experimentation from the end of 2025 until now, which is summer 2026. I considered making the project open source, but keeping it private for now. Please check the description to see if anything has changed. I believe that directionally it would be great for the SDR community to collect data like that, so I'll describe the steps I took to create the project. An SDR dongle is needed for autonomy. It's not strictly necessary to own it, because you can connect to existing feeds and read from there, but if a feed goes down or becomes restricted, you'd want to rely on your own device. SDR++ works great with the UI, but I needed something lightweight to run headless on a server. I used GNU Radio to read the feed and configured Squelch, gain, and other settings. I opened the feed on my server using Icecast. It generates an audio stream that we can tune into, and it creates a web page with a simple audio player. I connected to the feed and started processing the audio. I tried Moonshine and Whisper, both of them are open source transcription models. Moonshine failed my radio talk test, but Whisper performed pretty well. I could also run smaller Whisper models locally on a modest CPU. After transcribing the talk, I use an LLM, the so-called AI, to create categories, summaries, and geodata. An LLM and a prompt can significantly influence the output quality, and it isn't always about the number of parameters. I tried very small quantized LLMs on a CPU. The performance was slow, but some of them showed surprisingly decent results. I am using an API for the LLM now, but it's also possible to host one locally. Addresses also get processed against an address database, such as Nominatim. Since transcription isn't always accurate, I do a fuzzy match against a list of Burnaby addresses to correct mistakes. Incidents span multiple radio conversations, so I group them together based on a set of rules. Everything gets saved to a database, in my case it's Postgres. I use Docker to run independent containers for subtasks. Separately, I handle the front end with ReactJS, FastAPI, and an integrated map view built with Leaflet. If you want to make it publicly accessible, you'd need to buy a domain and host it. I use a VPS and serve pages with Nginx. You can also run everything locally with no exposure or dependence on the internet. The main dependencies include using APIs for transcription and an LLM. To run it smoothly locally without an API, you'd likely need a 6 or 8 or better 12 GB GPU. It may be possible to reconfigure the project to work without an LLM, but then you wouldn't get the nice incident summaries. As you can see, in its core it's exactly decode, extract, enhance, plot. or in other words, DEEP SDR. I'd like to discuss the ethical and legal implications now. From what I could gather, permissions for listening, processing, and publishing public safety radio communications may vary greatly by area. Many US states are quite permissive and allow you to publish what you hear. Canada seems more restrictive. While listening to unencrypted radio is still okay, publishing the exact addresses of incidents may violate the rules and can result in hefty fines. On the one hand, I kind of see the reasoning here. If I had a medical emergency and called EMS, I wouldn't be very happy with my private address and incident being publicly exposed online, especially since it could identify my family. On the other hand, I can see the counter-argument. Since this is a public service, funded by taxpayer dollars, taxpayers should be able to see how the money is spent. Also, for example, in Burnaby, the fire dispatch never announces people's names, but only the address. So it cannot be tied to a specific person, because it could be someone else living there or temporarily visiting. Ultimately, I'd be ready to share information about my address in exchange for being able to monitor the public service. There will be people with opposing views. From a technical perspective, we can ensure compliance with the publishing ban by redacting street names and masking the geopoints. We can mask the geopoints in two ways. The first is to randomly shift a point within a radius of, for example, 330 feet, 100 meters. This is easy and quick to implement, and it will help us maintain the incident density. The second way is to use hexagons instead of points. This is advantageous because it would also natively produce a heat map, so I would say it would be the preferred approach. This is my closing chapter. If you are interested in SDR, you don't have to rush out and buy a dongle right away. There are plenty of online resources you can tune into first. The main platforms include radioreference.com. It is a massive catalog of radio frequencies and trunked system data. Broadcastify.com, a dedicated sister site created by Radio Reference. It has thousands of volunteers who stream live audio feeds directly from their local receivers. Here is a sample of the LAPD radio feed.
10x44, 10x44, Wilford check, 15485 Ventura Boulevard, code 2, incident 1885, RD 1079.
OpenMHD.com. It is an interesting project that splits radio conversations into separate audio clips. Here is an example of marine radio near Vancouver.
Traffic, the vehicle carrier 8 for 8 is northbound at 1.82 knots for Port Angeles. Victoria Star 2 traffic.
LiveATC.net. This is a specialized streaming service focused on aviation and air traffic control communications.
Tower, respect Delta X-ray, downwind, let you go 26 left.
Quebec Delta X-ray, Roger, number 3, runway 26 left, follow Cessna right base, just east of Golden Ears Way.
To dive deeper, I highly encourage you to explore the radio reference forums, active SDR subreddits, the rtl-sdr discourse group blog forums, and the GNU Radio resources. I hope this provides a clear framework for building an incident map for your own area. If you need help, please reach out to me and we can discuss. If you are working on an interesting data project and would like to invite me to have a look, please also let me know. Check the description for future updates and my contact information. Please also give it a like and subscribe with the bell.